Okay, I'm back with an exponential decay problem. I'm first going to plug in 0. So 4 times 1/3 to the 0 power is the same as 4 times 1, which is 4. Let's pull out our first point. We'll make it blue. Our first point is 0, 4. Okay, our second point, let's go back to -1. When I plug in that -1, I get 4 times 1/3 to the -1 power. And 1/3 to the -1 power is the same as 4 times 3 over 1, so we get 12. Now, good old Mr. Ludd didn't plan well, but that point, 0, 12, is going to end up way off this graph. Way up there. Let's see here. Yeah, let's throw it way up top here. Hopefully you can see that. I don't know if that's off of the window. I got these two red lines that are cutting my screen parallel horizontally, and who knows, maybe you can't see that, but I'll stretch my graph to make it look nice in a minute. Okay, so here we go with our third point. Let's plug in 1, and when you plug in 1, you get 4 times 1/3 to the 1, which is 4 times 1/3, which is 4/3, just a little bit greater than 1. Let's plot that point here, and 4/3, that's 1 comma 4/3, right about there. Alright, so let's sketch a graph. Again, this is an exponential decay problem. As you can see, that base value is less than 1 but greater than 0. And again, now our end behavior to the right will approach 0 as x goes to infinity, and our end behavior to the left will go up to infinity. Alright, we got one more type of problem that I want to cover, and then that'll be it. Hopefully you're enjoying this, because I know I am. Okay, everybody, I'm back here. I've got an end behavior slide up here. I got a graph of an exponential growth function. As you can see, I've written out limit notation, and I am missing a few items here. So I want to talk about left end behavior and right end behavior. So think of end behavior as behavior on the ends. So as I go to the left forever, right, in this direction, I'm going to see if I can pull out my, there it is. Okay. What is this guy? Oh, lightsaber. Oh, yeah. So as we go to the left forever and ever and ever, what is this graph approaching? Well, an exponential growth function out here, that is going to approach 0. Now we need to write something in this area as well. Well, as x approaches what? What would go here? Well, pause for a second here and think about it. Now that you're back, what do we want there? We want negative infinity, because that means as x approaches negative infinity, as it goes off to the left forever, what does that function approach? That function approaches 0. Okay, so in the opposite direction, as x goes off to the right, as x goes off to the right, we're not following the function yet, we're just going off to the right. What is that function doing? It's going up. Will it ever come down? No. Does it ever level off? No. Is it going up and up and up? Yes. Is that like your GPA? I hope so. Okay, so as x approaches infinity, what happens to the function? It also goes to infinity. There's one good example of exponential growth. Alright, last two examples, and then I'll give you your homework assignment. These two functions here, f of x and g of x, one of them is a growth function, one of them is a decay function. What I'd like you to do right now is take 30 seconds, pause this video, and figure out which is which. Alright, now that you're back, on problem number 1, hopefully you identified that this is a growth function. This is a growth function with a b value that equals 2. Okay, hopefully that resonates with you and you got that right as you were looking at it. Okay, now in the second problem, obviously I told you there was one growth and one decay function. In problem number 2, the decay function just has a b value equal to 1 over e. Remember, e is about 2.71, therefore that decay factor is about 1/3. But we really don't care about exactly what the decay or growth factor is here. We just care that it's either growth or it's decay. So I'm going to sketch a general graph. I don't like red on that case. I'm going to sketch a general graph of this function f of x equals 2 to the power of x. So I'm going to be very inexact here, but as you'll see, the end behavior as x goes to negative infinity on this graph will be 0. For all growth functions that don't have a vertical translation, meaning was it moved up or down, if it doesn't have a vertical translation or shift up or down, that asymptote and that left end behavior should be 0. For its right end behavior, as you'll see, as x goes to the right off to infinity, as we've seen before, that function's limit will go to infinity. Now as we look at this decay function on the other side, I'm really not worried about the accuracy of this function, but I do know that it has no vertical shift up or down. Therefore I'm going to take my lightsaber here, and as x goes to the left forever, that function's value is going to go up to infinity. And as x goes to the right forever, oops, lost it. Oh, I want the lefty one. Here we go. There it is. Off to the right forever. That function will approach 0. You guys, that's end behavior. That's how you write end behavior. Don't be writing any function notation that doesn't look like I just wrote. This is the correct notation for end behavior. I'll have your homework assignment in the next slide, and you'll have time to work. Alright, I won't keep you long. Your homework is worksheet 6.1.2. I wanted you to do numbers 1 through 4. 6. Ooh, that was a bad 6. Let's do that again. 6, 8, 10, and 12 through 15. All of which will be possibly graded tomorrow, which will be Wednesday. We will grade 611 and 612. And just for the fun of it, may the force be with you, children. Have a nice day. See you tomorrow.